How's everybody doing today? Yeah? A couple thumbs up, sweet. Yeah? Oh yeah. Welcome to the ArcGIS Runtime, maximizing performance of your apps. My name is Ralf. I work on the Runtime core team. And this is Will.
Hey, as Ralph said, I'm Will. I also work on the Runtime core team.
You get a lot of insight to what we do with our introductions there. We work on the core. So what we're going to do in this session, we're going to talk about the new runtime architecture just a little bit, the version 100 architecture, because it is different than the older 10.2x architecture. And then we're going to talk a little bit about how do we actually measure performance. What does the things that you do when you make the decisions that you make in runtime, how that actually affects performance. And really that comes down to two major things. It's static mode versus dynamic mode. And we're going to explain what the modes are and how they work and how they render. And we're going to use our internal Runtime Core test app to show this and use NVIDIA Insight because it provides some really cool tools to analyze performance. And we run these tools every so often on our code to try to figure out, okay, what can we improve? Where can we improve our rendering performance? And then if there's still time, because I'm going to try to hurry through this so you guys can go off to the party. You guys are all troopers for staying and going to a 5:30 session. That's awesome. I'm going to try to show you a quick demo of some of the new rendering improvements that we're working on for the future. So the new architecture at Quartz, or version 100 of the ArcGIS Runtime, 100.0, basically most of the implementation has been moved down to C++. Like in the older versions, Runtime Core provided an API for the APIs themselves to bind onto, and then they built a lot of their implementation up at the API base level. But this kind of led to a little bit of discontinuity between the APIs, and every time we build something in the core, every API would have to rebuild it themselves up at the upper levels. So we've moved everything down into C++. That allows us to build functionality once, and then APIs just basically bind on top of that, and they can focus more on the things that are specific to the API, .NET framework stuff or whatever it is. And this leads ultimately to allowing us to build functionality faster. We also at Quartz, or version 100, did a public API redesign, which you probably have noticed if you've used it. The idea behind that is to unify the API across all the platforms so that if different people working on different platforms, they can talk to each other and everything is all the same. And we attempted to simplify the developer workflows. So if you've been to this session actually in the past, some of the things that we used to talk about aren't really available to you because we've simplified everything. You don't need to call this special function or do this thing a certain way to improve your performance. This is a good thing, and ultimately whenever we do improvements, everybody just gets it. That also thins the interop. So APIs like .NET and Java that have a pretty thick interop layer because you're going from C++ to .NET or you're going from C++ to Java, that's smaller, so this actually improves performance significantly. So the runtime display architecture is powered by the Runtime Core. We support at Quartz, at the version 100, DirectX 11, OpenGL of various versions, OpenGL ES2 and 3, and Angle, and that's specifically for Qt. It's an active display. It operates on a pulse. So this pulse happens, I think, every 15 milliseconds, but that's an API we expose to the APIs that they can kind of change. And every pulse, we determine what, if anything, needs to redraw. So if something does need to redraw, we execute draw commands on CPU and the GPU. And the time that this takes on every single pulse really is what impacts your frames per second. And as your frames per second start going down, your map starts to slow down, right? Because the frames per second, it's like a movie. If you slow down the frame rate, you get a slower moving movie or map. So really, I just kind of went over this. As more and more work has to happen on the GPU, as more data needs to be processed on the GPU, as more and more draw calls are set to the GPU. And I say loosely on the slide because some draw calls are cheap, some draw calls are expensive. And knowing which type of draw call happens when you do what will really help you improve the performance of your app. And that is the point of this session. So what else? Why are draw calls why are some so expensive? Well, aside from the fact that some have to do a lot more work than others, another major thing is the GPU basically, we write shaders and stuff to do execution on the GPU. And when you have to switch a shader, that's an expensive task that actually causes the GPU to stop what it's doing, because everything's asynchronous. It stops, it executes all the leftover draw calls, switches its context to the other shader, and then continues on. And state changes, you can't really escape a state change, but when they happen in the runtime, it's because we're drawing points and then we switch over to lines or something like that, or we're using tiles and then we use graphics. And you can't control that, but if you can minimize it, that's beneficial. We basically have two rendering modes in the runtime. So it's CPU-based rendering and GPU-based rendering. So the CPU is this beast, right? This powerful processing beast that you could throw anything at it and it's just choose at it and then it does whatever it needs to do. And it uses this huge vat of system memory. I mean, I guess some of your mobile devices don't have so much system memory. So it can just do a lot of stuff. But it produces a lot of heat and it drains your battery. So on your mobile device, if your CPU's churning away, you'll see that battery just kind of go down. And one of the things as a rendering engine for a mobile device is you have to think about heat because there's no fan on a phone. So how are you going to cool that thing down? The big old desktop's got these liquid cool systems and everything. They totally handle tons of processing. The GPU, on the other hand, is extremely efficient at a small set of processing, right? It has a smaller amount of dedicated memory. It might share system memory. A lot of mobile devices share system memory with the GPU and the CPU. So when it processes, uses way less battery and generates way less heat. So why do we have two modes, CPU and GPU, when GPU obviously sounds way better? It gets a little complicated because people who author maps for runtime author it on a desktop. And your desktop has tons of data sources you can work with. You could be trying to render 1 million features on your mobile device. Imagine trying to create 1 million features onto a GPU in GPU memory, which is, as I said earlier, which is smaller. You also have to transfer that data and create it on the GPU. That's a performance hit. Really, runtime has to work with any map that you throw at it. So the CPU can handle anything it gets thrown at, but it's going to cost you some battery life. So that's why we have the two different modes and allow you to choose what the mode is that is appropriate, so that you can render whatever data you need to. If you're going to render 5 million points or 5,000 extremely complicated polygons, maybe you need to use static mode for that because your machine is going to just fall over trying to render that in dynamic mode. So static mode, I actually started talking before I had the slide. Static mode is CPU-based rendering. You can think of it as on-demand rendering. So we only render when we need to, right? We create an image and we render it on the screen, and then you pan and zoom around, and when you're all done doing that, we'll create a new image. So the amount of data you use doesn't really impact what the GPU is doing because the GPU is doing the same amount of work all the time. It gets these images from the CPU and just puts them on the screen. Whereas dynamic mode, that's all GPU based. And you could think of it as in dynamic mode, we're always rendering that data. Every frame you're rendering that data. So this is really cool because you could do cool things on the GPU like moving points around, or when you rotate your map, like your labels or your symbols, like they stay screen aligned because it's just always rendering. But the more and more data you stick on the GPU, and if we go back to this slide here, this just, if you look at, as you start sticking more stuff onto the GPU, the amount of memory starts, you start running out of memory, and ultimately every frame you have to process more data. And I probably shouldn't have gone, because now I don't know where oh, here. So in static rendering mode for graphics, if we're talking about graphics, in static mode, we're basically rendering the graphics as paths on an image. This maintains your cartography, which is could be very important depending on what kind of symbology you're using, like advanced symbols. And advanced symbols are the multi-layer pro symbols that you can get. You can get these from feature services or military symbology. This is where, if your symbol doesn't look like it does in pro, this is not a good thing, right? We render this image, we break it up into blocks, so that way when you pan, we could just partially update the blocks. Partially update the parts that are missing, and we convert those into textures, push that to the GPU, and place it to render. This doesn't matter if you're rendering points, lines, or polygons, whatever. It doesn't matter what you're rendering. There's no state change required to render in static mode. In dynamic mode, on the other hand, we take the symbols and we convert those into textures, and we stick them on this texture mosaic, which you see kind of on the right side of the screen for you. And then we take the geometries of whatever we're rendering the graphics, and we convert that into triangles. And so the more complex your geometry is, the more triangles we're going to have to create. The more triangles we're going to have to create, that's more stuff that lives on your GPU. That's more work that you have to do on the GPU. And then at render time, we just apply the textures. So basically, because it's just triangles on the GPU with textures applied, if you need to rotate it or move it around, it just happens at every draw or every frame. The thing to note about dynamic mode, which is kind of important, is because we're trying to be as performant as possible rendering in dynamic mode, and we're working with textures, your point symbols, they just become like images, right? Put on this texture mosaic. Your line and polygon symbols get a little more complicated because they're supposed to become this texture, and we're not rendering the entire geometry all at once. So we take a snapshot of the symbol, almost like a Polaroid of it, and then just kind of lay the textures along the geometry. And this is extremely fast and looks good in most scenarios because we actually do a little bit of smoothing and inserting stuff when you have extreme breaks in your geometry. But as your symbology gets more and more complicated, it may not look exactly like it does in desktop. And it does require additional processing to really smooth out the symbols. So maybe polygons and lines, depending on what you got, depending on your device, you might want to be looking at static mode for that stuff. So I'm going to pass it over to Will, and Will's going to show a demo using NVIDIA Insight of static versus dynamic mode.
Cool, thanks Ralph. So as Ralph said, we're going to use our internal testing application along with NVIDIA's Insight so we can actually look at the draw calls that are made for rendering a canvas layer, or for rendering a graphics overlay in both static mode and dynamic mode. So first thing we're going to do is we're going to do this in static mode, and we're just going to draw a single point on here. So if I start up Insight, give it just a minute. So along the bottom, we've got the draw events that happened as we rendered this particular scene. So each of these blue ticks is a draw event that happened on the GPU. So the first thing we've got happening is we're laying down the background grid for the map that I'm showing. And then in this particular case, I'm using a tiled layer, so like an ArcGIS tiled service. In this case, it's actually just a local tile package. So first thing we're doing is the GPU is getting those tiles from the vector tile package, and we're just laying them down. So a couple of draw calls for that. Yep, yeah, it's a TPK, so a raster tile layer. We're going to talk about tile layers a little bit later, go into more of the specifics between a raster tile layer and a vector tile layer. So now we're going to start drawing the graphics overlay. And exactly as Ralph said, the way that this is going to work is the CPU has generated an image and passed it to the GPU. And now we're just going to draw everything that's on the image. So if you see the wireframe down here, we have already started drawing that image. And as I go through the draw calls, we get to the point where our image actually is, you can see our texture cache up here. So we've got the particular part of the symbol that we're drawing here. And we just iterate basically over the entire image that the CPU gave us and draw everything. So in this case, it looks a little bit like static was less than ideal because we had to iterate over the entire image when really we just had this little bit to draw. We'll go over why, but that's a pro and a con in just a second. But first, let's compare that to dynamic mode. All right, so we've got the exact same setup. We draw the background grid, we put down our tiles, and then we've just got a single draw call for this point. And notice here that it's focused, it's right exactly where we want our point to be. We've got our tile cache, or excuse me, our texture cache up here, and we draw our point, and we're good to go. So in this case of a single point, it looks like dynamic mode is the clear winner. It's better, it's more performant. That's not strictly always the case. So now I'm going to add 10,000 points to this layer, and we're going to look at what happens when we render this in dynamic mode. As soon as Insight catches up. All right, so same thing. We'll go through the tiles really quick. We draw our original point. And this is where you can start to run into problems in dynamic mode. So for each of those 10,000 points, we had to break those up into triangles, and then we had to transfer all of that data into from the system's memory into the GPU memory. So on this particular laptop, 10,000 points is no problem. On your desktop, it's probably no problem. But if you throw 1,000,000 points at it, you're eventually going to start exhausting your GPU memory, and that's where you start to run into performance problems. Or if you're using a low-end mobile device or something, even 10,000 points might be enough to cause you some hiccups. The nice thing about this is we only have to pay this transfer cost once. So for example, when I'm using dynamic mode, now that all of these points, or excuse me, now that all the polygons are into the GPU memory, I can animate this, and it's super fast and it's super quick because there's no transferring of the memory anymore. Everything's ready to go. So conversely, with 10,000 points in static mode, this is going to be the exact same workflow that we saw earlier. We've gotten an image from the CPU, and we're just going to render it. So I'm going to skip through I skipped a little further than I wanted to go. All right, so we put down our last tile, and we do the exact same thing that we saw when we were drawing a single point in static mode. We're just going to iterate over the entire image and put down our points. So the really awesome thing about static mode is, as Ralf was alluding to, whether you throw 1 point at it or 1,000,000 points at it, you're rendering the exact same amount of data. So if you're in a situation where you need to draw tens of thousands, hundreds of thousands, or millions of points, there definitely it's worth considering using static mode if that's a viable option.
Thanks, Will. Okay, so just to kind of drive a stake through this, static mode versus dynamic mode. As you saw, it gets a little weird because in dynamic mode there was only 2 draw calls that they had, right, or that we saw, but there's a bunch of stuff that had to happen on every single draw call, and every time there was those draw calls were actually state changes, right? There was that one graphic that showed, and then we had to swap over and do another one. Whereas in static mode, the CPU rendered the image and then just gives the image over, and those draw calls to render those little blocks, that's super cheap. So that doesn't really take anything. So really your GPU is not working hard, it's your CPU that's working hard. So CPU-based rendering, we call it static rendering. It only draws when it has to, and that's when you change, when you pan, when you zoom. We don't really draw when you rotate the map because we could just take that image and rotate it around. And that then gets pushed to the GPU during one of its pulse cycles. So on the GPU-based drawing, the map is just constantly checking, do I have to draw, do I have to draw, do I have to draw? Oh yeah, I gotta draw. And all the data that you have there is always drawing if you have data there. It just may not have to update anything. So the more stuff you have to do on every single pulse, the lower your frame rate will go. This is really evident with this example that we're going to show here of polygons. So if you have a polygon in dynamic mode, it's effectively 2 geometries, right? It's the polygon and then its outline. Drawing a point or drawing a polygon and then drawing a line is a state change. So that's an expensive switch, right? And because it's a line and a polygon, that's a lot of triangles that we got to push to the GPU. Is that really a big deal? Most of the time it's not a big deal because the GPU is designed to render lots of triangles, but as it starts getting bigger and bigger and bigger, it starts getting more and more stuff to process, and depending on your device, that could be a problem. So is it always going to be a state change with outlines and polygons? Not necessarily, because what we have done is we've enhanced we've added some functionality to shader. So if you're using simple based outlines, like ones that you could do programmatically through the runtime, that is the same shader, so there's no state change required there. But if you're using advanced symbols, like you're pulling it from Pro or from a service that's using advanced symbology, so these are like your more complex multi-layered symbols. So you have like a line, and then you have a dashed line on top of that, and maybe you have like some other stuff on top of that. It's made up of multiple layers. That we have to use the older shader. So because it's more complicated, we have to do a little bit more work to make it look correctly. Whereas in static mode, it's the same no matter what, because the CPU processes that stuff and then pushes those images to the GPU. So I'm going to pass it back to Will. He's going to show this in action.
All right, so all I've got here is from a geodatabase, a bunch of polygons comprising the United States. So right now this is set up in static mode. And as Ralf said, this is going to be we're kind of going to beat a dead horse here, but this is going to be exactly what we've been seeing so far. We're just going to iterate over the image and the image that the CPU gave us, and put all of that. The GPU is just going to put all the textures onto that image. So no additional costs incurred here. Kind of, like I said, exactly what we expect. And if we zoom in and out on this, there we go. If we zoom in and out of this, you can tell that it's static mode by the way that when I zoom in, for example, the CPU everything kind of blurs because we're resampling while the CPU is actually re-rendering this for us. So now if I switch this into dynamic mode, we don't see that same blurring anymore because the GPU is rendering all of this for us live. And right now this is really, really performant. And the reason for that is exactly as Ralf said. Since we're not using advanced symbology on the outlines, all this can be rendered by a single shader. So all we have to do is take all of the CPU turns the polygons into triangles, and then the GPU just puts those triangles into place and adds the correct textures to them. So single draw call, and we've drawn the outline and the polygon. But if I stay in dynamic mode and I switch this to an advanced symbology outline, right off the bat we see that it took a second there to render all of this. Most of the states changed immediately to this peach color. A couple of them are still green. And it becomes really, really noticeable if I start trying to zoom in and out. You see that it should be a nice, smooth zoom in and out is what I'm trying to achieve with my mouse. But we've got a little bit of a hiccup going on as I'm doing all this. So the reason for that is exactly as Ralf mentioned. In this case, because we're using advanced symbologies, for each of these polygons, we render the individual polygon, and then the GPU has to go through a state change and render the outline. So we've got, in the last case, we had a single draw call. Now we've got a ton of draw calls. And as we step through them, so we see the first thing that we're doing is we're rendering the triangles for Hawaii. And then we state change on the GPU and render the outline for Hawaii. Then we render the triangles for Washington State, and then we do the outline for Washington State. And I'm not going to do all these because I'm not that good at my states, unfortunately. But as you can see, for all 50 states, we're going to do the polygons for the state, and then we're going to do the outline for the state. Conversely, with advanced symbology, if I switch this back to static mode, we see that we're in static because there's that unfortunate blurring as I'm zooming in and out while the CPU is rendering the image to pass to the GPU. But the nice thing is that the draw call is going to look exactly like we've been seeing throughout with static mode. All we're going to do is go over the image, and for every block in the image, we're going to throw down the appropriate textures. So exactly as Ralf said, if you need to use advanced symbologies for a shape like a polygon, definitely worth considering using static mode. This is actually a pretty good GPU in this laptop, and it's still brought down by these polygons.
Cool. Thanks, Will. I was going to make a joke about you not knowing your states and working for a GIS company.
That's how I roll.
Then again, I can't spell, and I blame Word. Because it fixes everything for you, right? No? Okay. So what about static mode? So how does this apply to my base maps? How does it apply to tile rendering? You can think of raster tile layers as the static mode of tile layers, right? And raster tile layers are just a collection of tiles that are processed by a desktop or ultimately pushed off to a server. You can get a collection of those tiles in a form of a TPK, and they perform extremely fast because all it is an image that we just grab and we push it to the GPU. We don't even have to do any processing on the client side to render tiles. Vector tile layers, that's like more the dynamic mode of tiles, right? It's a bunch of compressed vector data and a symbology sort of specification that we have to download or load from the VTPK. And then we push that data onto the GPU, and the GPU has to do all this work to render it. So one of the things to think about, though, with raster tile layers is raster tile layers are images that are cooked at a specific DPI. So I believe there are ways that you can cook it when you publish a service at a higher DPI. But you need to think about this when you're using a mobile device, because your mobile device's resolution is like really high, right? And if you, by default, if you cook your raster tiles at 96 DPI, if you want to preserve scale, they're going to look kind of blurry on your mobile device. And they're also pretty large, right? It's a bunch of images. So, you know, those ArcGIS online services can get up to terabytes in size. So, yeah, basically, the other thing that you have to think about is with raster tiles, one of the advantages is that whatever your map looks like, if you're going to author your own raster tiles, you just create a raster tile layer out of it. It doesn't really matter. You don't have to do any special stuff to make your map look good because it's just cooking images. One of the things that we did at version 100, we made raster tiles behave slightly different depending on what layer collection they're in. So if you've used the version 100 code at all, you could see that there's different layer collections. There's base map layers, operational layers, reference layers, and graphics overlays. So depending on where you put your raster tile layer when you load it, depends on what kind of behavior it's going to have. And we did this for a reason, right? Things that live in the base map layer collection are generally things, continuous data, continuous raster data if it's a raster tile layer. So you want that thing, when you pan your map really fast, you want to always see something, right? If it's blurry, like if you use any sort of mapping application and you pan really quickly, it's blurry, but you don't see the map background. And then slowly as the tiles start coming in, it fills in the space. We call this behavior skin of the earth style rendering. And what we do is we hold some of the coarser textures in memory, and if we zoom to an area where there's no tiles, we just resample that texture and use that texture to fill in the display. And as new tiles come in that are for that area, we'll replace that texture with the new texture. If you stick your raster tile layers in the reference layers collection, this is like a totally different thing. If you've worked with reference layers using like some of the ArcGIS online services, they're generally like labels or outlines. They're for your reference, right? They're not like continuous coverage data. So if we were to do the same behavior in that collection, that would look horrible. You'd zoom in, because most of these are highly transparent tiles, right? There's just a little bit of stuff in there. You zoom in, it would be like this blurry like word that you're trying to see, and then it would like eventually clear up. So what we do in that situation, we just clear out all the tiles and just render the tiles that are needed for that scale, that LOD. In the operational layers collection, so there's a lot of workflows that use operational layers, raster tile layers and operational layers. We do sort of a mixture of the both. We don't clear it out, otherwise you'd see your map flash, but we use a coarser tile till you get the newer tile, but we don't go as high as in the base maps layers collection. So vector tile layers. Vector tile layers work great on high DPI devices because it's just vectors and we just render it locally on the device. They're really tiny because it's vector data, it's not this huge image. So if there's no data there, there's no data there, right? And also the vector tile layers you have an option when you author them to index them. So we don't actually create a tile for an LOD if we don't need to. Instead, we use the tile above and just over zoom it. So it's makes the data even smaller. And it's dynamic too, right? If I have labels or if I have point symbols and I rotate my map, everything stays screen aligned and the labels have deconfliction, so they'll get dropped if they start to cover up other labels. But the performance of vector tiles is entirely focused on the data. If you take your map like you did with raster tiles and just export it to a vector tile layer, first off, there's some things that won't export, like raster data. And the other part is, you might have like 100, if you have 100 layers in your map, that's 100 layers that we have to render on the client. That's gonna render pretty bad, right? That's a lot of stuff that we have to process. So proper authoring of your data when you're creating vector tile layers is really critical for performance. And Will's gonna actually show us now some maps and some differences in how the two different modes render.
Cool.
Layer types.
Thanks, Ralf. So the first thing we're going to start with is I've just got a raster tile layer here. It's the street space map from ArcGIS Online. And as I dive into this, I just want to point out that, again, this is our internal test application. We have made no effort whatsoever to make this performant with network requests. And so for most of the demos, I've been using local data sets on the disk, just so nothing can go awry. In this case, I didn't have any access to any TPKs that showed a wide enough scale range so we could really demonstrate the skin of the earth stuff, and we really wanted to show you guys that. So I'm going to be going on network. If this is really, really not performant, please forgive me. So like I said, we were starting out with just a raster tile layer, and so if we immediately, you see me zoom in, and we saw that we still had something to render. It was kind of blurry because we were using the tiles from the very lowest LOD or the very highest scale range until we actually pulled in the new tiles. If I zoom in even further, maybe a little too far, we see the same kind of stuff. If I fling it further than that, not out into the ocean. But yeah, I guess as you see, as I zoom through and try and fling around the map, we're still showing something even if it is resampled and kind of blurry because it's from a lower LOD. And the drawing performance of this is going to be what we have been seeing since the very first demo. So again, because we're using a raster tile layer in this case, all we do is we get the images from the service, and then the GPU just chunks them up, the service actually chunks them up in this case. So all the GPU has to do is put them into the appropriate place and texturize them for us. So 4 quick and dirty draw calls here. And that's not going to change no matter what I do here. I can zoom way in. I'm going to try and stick to around Italy and Sarajevo. So I've zoomed in. We've got a whole bunch more detail than when we were at the world scale. So we're going to have a couple more tiles, obviously, because we're zoomed in much further. But the draw performance, we're still kind of within the order of magnitude for even being at the world scale. All we're doing is getting tiles from the service and putting them down. And kind of as Ralf mentioned, you can think of the raster tile layers as basically the static mode for tile layers. So for example, the labels that we're seeing here are actually baked into the tile. So if I rotate this map, they are not going to rotate with this at all. And before I move on to the vector tile layers, I'm just going to go to a reference layer really quick to demonstrate the difference in the skin of the earth stuff. So here we're out at the world scale. We've got some labels that are drawing, and if I zoom in further to North America, you see that we didn't get any blurring. We didn't resample the coarser grained tiles until we got into the United States. Because we don't want to give you that horrible experience of the labels just being a blurry mess on your screen. So these guys only show up, we specifically only request and draw the tiles specific to the scale that you're at when we're working with the reference layer. So now I'm going to switch over to a vector tiled layer. So as Ralf said, since we're doing all the rendering for this on the disk, we're taking basically the rules for how this should be drawn, and then we are drawing it on the GPU. So looks awesome on any device, any DPI device, whether it's a Retina display or a really low resolution display. And since these are dynamically drawn, if I rotate this, we see all the labels will adjusted to be displayed relative to the screen. The drawback is that since we're doing all the rendering for this on the device, that can get a little bit expensive. So even here at the world scale, you can see we've got some continents. I can kind of see some areas that are probably national forests or large forests. And in the ocean, I've got a couple of different shades of the ocean. And unfortunately, each of those is going to have to be a separate draw call. So, oops. All right, so we put down our background grid, and you can see right away, we start out by drawing most of the continents, and went a little too far. Then we're going to pick up Greenland and Antarctica, start going into some of our larger forests, some other forests, do the ocean, slightly different color of the ocean, and so on and so forth. You can just, like, cartographically, this is a really beautiful map, and that's great if that's what you want to display. Just be aware that you're paying for that because you're rendering all of that locally. So if you have a low-end mobile device, again, this might not be your top choice. And this is just going to get worse if we zoom in from a performance perspective. Obviously, the map will still look beautiful. So we saw with the raster tile layer, this was 16 to 20 tiles that we had to put down. If I do this with a vector tile layer, we've got 2,000-ish draw calls. And again, I'm not going to go through all these, but just want to demonstrate that all we can do is take similar polygons, break them up into triangles, and render them before we have to state change on the GPU. So that is exactly what we see in these thousands of draw calls. So there is kind of a middle ground if you know that you need to support a wide range of DPIs on devices. Obviously, if you need a really detailed base map like this, there's nothing getting around it. Hopefully you have access to some pretty beefy GPUs. But if you don't need quite this much detail, a great thing to do is to consider a base map with a little bit lesser detail. So that was the world street map vector tile layer, and this is the dark gray vector tile layer. So right off the bat, drawing this at the world view, or excuse me, at the world scale, we can see that we've got substantially fewer draw calls than even the last map had. So we're going to put a background down. We do all the continents at once, and that's all we had to do. Super, super simple. And even if I zoom into Sarajevo in Italy, it's going to be more calls than we were doing at the world scale, obviously. But because this map isn't as cartographically complex, it's still going to be much more performant than that really complex, really beautiful street map was. So you can see just from looking at the density of the lines that we've got maybe half as many draw calls on here. And kind of the same thing as we go through. We put down the background, and then we just kind of start drawing polygons as necessary. So kind of a summary, the vector tile layers are beautiful. Just be aware that if you need to, they'll look great on any DPI device. Just be aware that the cost for that is that you're rendering everything locally.
Cool, thanks, Will. And the same sort of concept applies. You can mix and match vector and raster tiles, right? Maybe you want to author your maps where all the polygons are just your raster tiles because you don't care if they look so blurry when you're zooming in. And then just use the roads and the points features for your vector tile sort of layers. I'm going to talk about one more thing, and this might be kind of coming out of nowhere, but it's actually kind of an important thing for performance in the runtime, and that is fonts. Why are fonts important, or why do they have a performance impact? So if you're rendering stuff with tons and tons and tons of labels, or you're doing a bunch of text symbols. Well, one of the things that makes a runtime kind of interesting is, especially when you're authoring maps with desktop, or you're authoring maps that are going to be used on any device, every device doesn't have the same fonts. So if you pick a font that doesn't exist on the device, before, you would just get a box. Now we've actually implemented ways to fall back. So if you choose a font that doesn't exist on the device, we'll find one for you on the device that will fill that, will make that glyph. The problem is if you start mixing languages within your text, then we have to, and that font that we found doesn't have that glyph that we need, we have to find the next one that actually has it, and so on and so forth. So if you're using if you're using a lot of text symbols, if you're using labeling, and you're using fonts that don't exist on the device, every single time we have to render the text, we're gonna take a hit, and it's not going to be that great. So since we still have a little bit more time, and there's still time for questions, I kind of wanted to show a real quick demo of a sneak peek of some of the stuff that we're working on. Or actually, we're working on new ways of renderings, right? So we're trying to make dynamic mode more and more comparable to static mode, so you can actually throw more and more stuff at it. Ultimately, what we're trying to do in the future is make the functionality that we provide to you scalable based on what you have on your device. Right now, Runtime ultimately has to work on a wide range of devices, so we're kind of locked into lower end devices, what they can do. But we're currently working on making our functionality scalable, so if you've got a really bad low-end device, well, maybe you just can't use that piece of functionality, or you fall back to a CPU-based rendering for that piece of functionality, and we could use GPU-based rendering for newer devices and newer stuff. So, but just kind of like, I guess, whet the appetite before you guys go off to a party, I wanted to show real quick, thanks, Will. This is like totally alpha. This is something we're working on, and I think it's really cool because it really, if you look at your frames per second right now, right, when we're just rendering a TPK, we're hovering around 80 frames per second. That's pretty awesome. So now if I were to add, this is our new rendering mode. It's not going to be available at update 1, or maybe it will. I don't know. We'll find out. We'll see how far we get. But what if I were to add 100,000 graphics in dynamic mode? Well, we're still at 80 frames per second. And if I pan and zoom, I mean, our frame rate doesn't really go down very much. So let's add 200,000 graphics. Oh. Look at that. This mouse is freaking out, sorry. My frame rate's still pretty awesome. I'm still hovering around 80 frames per second. What about, okay, I can't even see things anymore. What about 300,000 graphics? What about 400,000 graphics? What about, I'm gonna see if this crashes, 500,000 graphics? You can see that, okay, our frame rate is kind of dropping down, maybe in certain scenarios. What about if I start adding some moving graphics that you can barely see? If I zoom in really close, there's moving graphics. That's 10,000 moving graphics. I'm still at 81 frames per second. As I start to zoom out, though, I've got more data to process, so my frame rate starts to drop, right? Because, like what we were talking about, there's more and more stuff to process. But this is some of new rendering technology that we're working on. We hope to get it in by update 2. It really kind of makes this presentation kind of void, I hope. That'd be really cool. So that's it, really. That's all we got. Thank you. If you please feel free to ask us any questions that you may have.